So guys, welcome back to the wireless channel. Today we'll have a talk by Dr. Eric, I mean, Hyun-Sok Roo, that goes by Eric about his work on affine frequency division multiplexing for 6G. Eric, please take it away.
Okay, so hello. This is going to be a first video of a three-part series on this affine frequency division multiplexing waveform for 6G. It's a new waveform that is being recently getting a lot of interest. And this first part will be going through the signal processing and the effective channel analysis of the AFDM signal in comparison also to the conventional OFDM over what is called the doubly dispersive channel. So first, to give a brief background on the motivation of this presentation, we have recently published two papers, or one published, one on archive, on this AFDM, proposing it as a very good candidate for 6G wireless systems. And in these papers, we do a lot more analysis and derivations and a lot of illustrations as well regarding why this AFDM is good for in doubly dispersive channel with high mobility and high frequency, and also a bunch of other analysis comparisons with the OTFS and OFDM as well. So here is just a reference before we start the presentation. So as I mentioned, the three-part video is a three-part series is on the first part is what we are going to do today. It's the signal processing and effective channel analysis. And in this part, we go through the derivations, the mathematical derivations. And in the other two parts, the second part, we go through in the AFDM waveform in detail and describe and highlight its properties, its features, and perspective towards standardization in 6G as well. And then finally, part three, we also talked about some related or enhanced waveforms that are based on the affine domain or the chirp subcarriers of the AFDM. The first one is called the chirp permuted AFDM or CP-AFDM that is going to enable a bunch of new multifunctional applications based on the AFDM. And then also something called the affine filter bank modulation. It's another waveform that combines the benefits of the AFDM waveform in terms of its full diversity and robustness over doubly dispersive channels, and also achieves, in light of the filter bank part of the waveform, very low PAPR and almost perfect out-of-band emission. So going to the motivation of the whole presentation and the AFDM, we know that, as we know with the well-known IMT 2030, as on the right figure, we know there's very good objectives that are highlighted. For example, the immersive communications, which relates with peak data rates, massive communications, which is the device density, and also hyper reliable and low latency communications, which is to do with error rates and latencies. And these triangles in green are extended from the 5G KPIs. And also on top of that, we have the ISAC, integrated sensing and communications, also the integration with AI within communication systems, and also ubiquitous connectivity. And all of this requires a bunch of new technologies or also implies a lot of different applications and assumptions. For example, this means that we will definitely go into higher frequency bands such as millimeter wave and even sub-terahertz or terahertz. All of these applications will also mean that we will be subject to more heterogeneous and dense multipath environments of the wireless channel. And also the keyword is multifunctionality. So we have integration of sensing, integration of computing, integration of physical layer security, and so on. So one of the most highlighted feature of these 6G or beyond fifth generation wireless system is the doubly dispersive channel. I mentioned before that we have a heterogeneous and a very dense environment, such as on the figures on the right. So this non-terrestrial networks or urban V2X scenarios, we have many targets or scatterers in the environment that are moving with high mobility, so high velocity. And this means that the wireless channel exhibits both time dispersivity and frequency dispersivity. This is also respectively the frequency selectivity and time selectivity of wireless channels. So these channels with some figures on the left result in a heterogeneous and mobile, so time variant multipath channel. And each of these scattering paths, for example, I can point the pointer. So one path, each of the multipath results in a scatter due to a mobile target, and this mobile scatter target means that each received path is going to have some fading coefficient that can be described by a complex number. This is typical, analogous to the channel coefficient in typical MIMO SISO channels. And then in each of the paths, we have a path delay that is denoted by Doppler. So Doppler shift, sorry, tau delay, path delay by this tau, which is from 0, of course, no delay, to some maximum delay, tau max. And then we also have a Doppler shift due to the velocity of the target, which is denoted by this nu of p. This p is for each p path, so there will be multiple paths. And then Doppler shift because the velocity can be both negative and positive depending on the direction with respect to the observer. We can also have some negative maximum Doppler and a positive maximum Doppler. And of course, you can see that each of these paths, because they encode the information of the path delay and Doppler shift, we can use this later for radar parameter estimation, which means that they can be used in ISAC. So the communication signal or the path has information about the radar parameters of the target. So this doubly dispersive channel is described mathematically using this time variant impulse response function, or TVRF, and this is denoted by this h of t tau. And this consists of a summation of multiple paths, so p is number of paths. And then we have the different parameters we saw before, the fading coefficient h, the path delay, which appears in this delta as an impulse. And then the Doppler shift is denoted and appears in this fast varying time dependent. So this t is instantaneous time dependent. That's why it's called the time variant impulse response function. And one way to observe this in a nice way is to take the Fourier transform over the delay domain. So this delta function becomes another exponential, and this becomes a fast varying function in both time and frequency. So we can see the time axis and the frequency axis, and the rate of this change is denoted by our Doppler shift factor and the delay factor here. So this is known as the time variant transfer function in time and frequency. And we can see why that this channel results in a very difficult environment for communications. But one other way that we can observe this doubly dispersive channel is instead to take the Fourier transform over the Doppler domain. So here, the time to the Doppler domain, that results in this exponential term to go to another delta. This now we have two delta functions, each with respect to the Doppler and the delay. And now we have a very nice looking shape of the function called the Doppler variant impulse response function. So one axis is the Doppler shift, the other is the delay. And now we have p number of impulses that are directly correspondent to the each path's delay and Doppler. So this Doppler variant impulse response function is also the foundation of what is called the delayed Doppler waveform, such as the OTFS. So when we actually perform some signal processing over these doubly dispersive channels, so we have some transmit signal SFT, and we have some additive noise, and the channel is described by this time variant impulse response function that we saw before. We know that this has to be represented in terms of a convolution between the channel and the transmit signal to form our receive signal. And this means that the convolution is denoted by this integral here, and here I've replaced the full formation of the time variant impulse response function from before. And we can see that this integral, when we actually take a discrete version of this continuous form, so when we sample the entire signal at the sampling frequency f of s, or in terms of the sampling interval t of s, we can get the equivalent discrete convolutional form of this convolution as r of n, the different n number of samples, and we have this discrete summation over this discrete convolution, where now the deltas has become this sinc function, and we know that this delay and the Doppler has been normalized with respect to the sampling frequency. So we can see that the terms appear as the Doppler shift divided by the sampling frequency, and the Doppler and the path delay divided by the sampling period. So this is what we had before. And one assumption that we make is that the sampling frequency, so the sampling interval, especially this T of S, is fast enough, so the frequency is high enough such that when we take the division of this normalized delay, this normalized delay can be approximated by an integer with negligible error. So this raw division is equivalent to this floor division such that this normalized delay is always going to be an integer. So we denote this normalized delay by L of P, defined here. And this is always going to be either 0 or positive integers. And the normalized digital Doppler shift, which we denote by this term here. So this nu of f of s, and we also add a term n for the digital Doppler shift. And that means we can now insert these two normalized terms back into our form, and we get this normalized delay Doppler version of the convolution, where now we have this f of p and L of p here. And now, because we've made this integer approximation, these sinc functions, they only appear at integer multiples of L, and that means the sincs are equivalent to their maximum height, which is then also a delta function. So now this is our final form. And when we perform communications over or transmit a signal over this convolutional channel, we assume that we have a prefix before attached to this transmit signal. So if our transmit signal sequence is of length n, we have s in some complex value of n. We have s0, which is the first element, first element of the sequence, and s minus 1, which is the last sample. We have some prefix that is of length n CP, so from S1, S minus 1 to S minus NCP. And this first assumption is that, or first requirement is that this length of the prefix has to be equal or larger than the maximum delay. So to ensure this prefix wraps around correctly, even with the maximum delay of the transmit signal. And this definition of the prefix elements is given here. So we have the element of the last term. So we have, if this s minus 1 means that it's the same element as the sn minus 1 here, but also we have a multiplication by this phase shift function. For now, we assume that this is just equal to 1 because this phase shift is determined by this prefix phase shift function, phi of Cp. And this for classical waveforms that are non-chirp based, so OFDM and OTFS, this function is equal to 0, such that this exponential is simply 1, and such that these prefixes do not have a phase shift and are equivalent to the exact elements in the last parts of the sequence. So given the prefix, now we can rewrite the discrete convolution form into a matrix using a circular convolutional matrix, and that is given by this equation below here. So this is simply the rewritten version of the previous discrete set. Now we have the transmit signal, which is a vector of length n, so height of n rows and 1, and the received signal also as well. And this channel H is the channel matrix, the convolutional channel matrix that is of n by n. And it is composed of what we had before, all of the terms. So first term is of course, the summation over the different p paths. And each path is composed of the complex fading coefficient we saw before. This phase matrix, which composes of the additive phase that we saw before. So this I mentioned for the OFDM and the OTFS is simply 1, such that for these two waveforms, this prefix phase diagonal matrix is simply an identity matrix. Then we have what is called the roots of unity diagonal matrix. So this matrix W is a diagonal matrix of the smaller vector W. This vector W is the roots of unity of n, so n roots of unity. So we have 1 and all of the endpoints around the unit circle. And then this unity is taken to the power of our previous Doppler shift value. So actually all of the elements here would actually also have an exponent of f of p. And then we also have a forward cyclic shift matrix denoted by pi. And what this does is every power of this matrix, so power 1, power 2, it results in a forward cyclic shift. So it shifts the matrix 1 to the left, the diagonal to the left, or down, depending on the way you look at it. So pi to the power 0 is the identity, so 0 delay shift. Pi to the power 1 is the delay shift of 1, which shifts the matrix, the diagonal, to the left. Or in terms of the effect on the signal, This means this is shifting the matrix of the coefficients to the right. So this is, and then LP here is the effect of the delay. So the delay terms that we saw before, which is always going to be integer. That's why this satisfies the integer power of the matrix. And then with all of these coefficients and the parameters of the channel, we have defined the circular convolutional channel. And then we can also define intrinsically this H of P, which composes only of the p-path components of the channel. So now this is the formulation we have received at the end of the channel, which now has three p parameters. So the first p parameters correspond to the channel coefficient. The next p parameters correspond to the delay of each path, and then also Doppler shift of each path. And all of these internal parameters are predetermined. So how we can perceive this is that each PHP is a superposition. So the total channel P is a superposition of P diagonal matrices, which are shifted because this phi matrix, which was the prefix, and also the roots of unity matrix are both diagonals. And then we're shifting that diagonal by this given pi matrix, which is the diagonal shift matrix. So each diagonal is shifted by LP indices to the left, as you can see here. And also Doppler shift FP does not change the position of the diagonal, but only shifts the phases of the roots of unity in the W. And you can see that because the shift is only determined by the L of P, the Doppler of the path delay, the diagonals of the path will fully overlap if they have the same path delay, and they will have, even if they have different Doppler shifts, the diagonal lie on the same off diagonal. So that is with the fundamental convolutional channel without any transform applied to it. So we can see this effect visually just for better understanding. If we have L equals 1, which is, or L equals 0, which is no delay, we can see that the diagonals lie perfectly in the center as with the identity matrix. And when L is equal to 1, we can see that the diagonal has shifted one index to the left. And for L equals 2, which is two shifts, they have shifted twice to the left. And conversely, when we have now no delay, the diagonals are lying always in the middle. And now we change the Doppler shift. We can see that on the left subfigure, we have the real part of the channel. At the right part, we have the imaginary part of the channel. When the integer Doppler is 0, we have this roots of unity is taken to the power of 0, so they're all equal to 1, and there's no imaginary part. But now when we start to add some complex, so when you start to add some integer Doppler shift, then we start to have this roots of unity such that they are going over the complex plane in a single. This is the normalized n roots of unity. And then as we increase the Doppler shift frequency, the roots of unity have different phases and the phases are increased. So and they can also be seen in the positive and the negative Dopplers. So they have the same phases, but they have different imaginary components, and they're fully differentiable in the complex domain. And of course, we can also have some fractional Doppler shifts. Now we have this f of p is non-integer, and then we also have the same effect that the roots of unity are shifted, but they're no longer fully periodic in the complex domain, as you can see with 0.5 or 1.8, that they do not fully wrap correctly. So going back to the channel, as we have understood the behavior of the effective channel, we can see that this is simply given a signal of S is equivalent to a left circular shift by this L of P, of course, with some effect of the prefix, but for now we forget about the prefix. So we get a left circular shift by LP indices, then a phase ramp. So this phase ramp is a diagonal matrix, and we apply this phase ramp of slope F of P. And then we apply complex fading coefficient, and that added, of course, with the noise vector, we have our received signal. So this comes very important later when we compare with different received signals, or the input-output relationship of different waveforms. So now we can see first a shift by the delay, a phase of f of p, the Doppler, and then a complex fading coefficient. So of course, based on that, we will now analyze what happens when we do an OFDM signal. And see the full input-output relationship. So of course now for the OFDM, our signal S is not some complex number. It is going to be the symbol vector X, which is coming from some constellation, for example, or it could even be some Gaussian signal, but we modulate this using an inverse Fourier transform of N. So this is an endpoint inverse Fourier transform. And this is the total signal that is transmitted, and that is transmitted over the doubly dispersive channel that we have seen before. And this gives us the received signal of the OFDM. And of course, we can demodulate this received signal. This R of OFDM is multiplied by the forward Fourier transform, endpoint Fourier transform, and we get the demodulated signal Y OFDM. And we get this full left and right multiplication by the Fourier transform matrices. And also the noise we have multiplied by the demodulator, but because the Fourier transform is a unitary transform, this does not change the statistic of the noise. So this is simply some rotated noise. And now we define this effective channel of OFDM as including the modulator and the demodulator. And of course, this complex coefficient can be taken out. And what we want to see now is what is the behavior of this inner matrix, inner set of matrix, especially what is the effect of right and left multiplying this convolutional channel that we have seen before with the integer shift and Doppler phase ramp after the Fourier transform. And that is going to be shown next. So first, again, OFDM, I mentioned that the phase matrix is simply an identity, so we will take that out. So now we have this form, the inner matrices is what we want to see the behavior of. And also for the sake of derivation, I've taken out the dependency of the path and the complex coefficient. So now see we have the Doppler ramp and the phase shift, the delay shift, and left-right multiplied by the Fourier. So the first thing that we can perform is now just rewriting this W explicitly as a diagonal matrix of this W. And this W is the root of unity, as we remember, and now it's element-wise power of this Doppler. So all of these terms will now have the FP in the exponent. And now by taking this identity, of course, taking the Fourier conjugation, which is equal to the identity, we can place this matrix in the middle. Now this is decomposed into Fourier conjugation of the diagonal matrix W and the Fourier conjugation of the phase shift, the delay shift matrix here. And each of this, actually, after this Fourier conjugation, the identities yield that, first looking at the right, the delay shift becomes a phase ramp of the delay value. So now we can see that this W, which is the same root of unity, is taken to the power of this delay factor. And then again, this diagonal matrix conjugated with the Fourier matrices yields a circulant matrix whose first column, so this is the circulant matrix, whose first column is given by the Fourier spectrum of the diagonal. So we have this diagonal vector in the middle, and taking the Fourier transform yields the first column. And then the remaining columns of this matrix is simply a circular shift of the same Fourier spectrum. So what this means, this circulant matrix, when we have integer Doppler shift, so this Doppler f of p as integer, this means that the Fourier spectrum of this roots of unity will be a unit delta given by the position at f minus p. So the first column will have all zeros except 1, whose value is given by 1 over square root of n. And that value will be placed at the minus fp position of that. So, and everything else is a circular matrix, so a circular column. So that means that this reduces the circular matrix to a circular shift, and whose shift is given by minus fp. So this is what we get from this first part when you assume integer Doppler. For fractional Doppler, we have not a unit delta, but the spectrum would give us a Dirichlet kernel, which is also centered at f of p. So this is close to a unit delta, but has some fading leakages on the left that is given by this Dirichlet kernel with the ratio of the signs. And this now we can represent this as the original matrix and just left and right conjugated by the Fourier for the sake of representation. So we saw again for taking the integer Doppler case and just assuming that the fractional Doppler case will be the same structure as the integer Doppler, but with the Dirichlet kernel-based leakages around. We can see that the OFDM is now given by a phase ramp of the delay factor, and then a left circular shift by the Fourier of the delay, the Doppler shift factor here. So now if you go back to the original doubly dispersive channel, we can see that the effects of the delay and the effect of the Doppler has swapped. So now the phase ramp, which used to be dependent on the Doppler, is dependent on the delay, and the circular shift, which is dependent on the delay factor, is now dependent on the negative direction of the Fourier in the Doppler shift. So by this structure, we can see that when there's no Doppler shift, so there's no left circular shift, that means the effective channel of the OFDM, because you're only applying a phase ramp, is completely diagonal, which is what we know from classical OFDM subcarrier orthogonality conditions. But when we now have Doppler shift, we have off-diagonal terms that are appearing, especially with fractional Dopplers, and we have now intercarrier interference, and each diagonal will overlap if they have the exact same Doppler values, because the shift is purely determined by this Doppler shift. And now what this means, the second assumption of the second, the implication of the second is that multiple paths are lying the same diagonal if they have the same shift, and that means that the OFDM cannot achieve full multipath diversity if there's p paths. So this is the biggest challenge that OFDM has been known for, and then to mitigate this, we bring in the AFDM, which is a generalization of the OFDM signal. So OFDM are multi-carrier that is based on a sinusoidal subcarrier, so all of them have constant frequencies over time. And AFDM, the affine frequency division multiplexing waveform, generalizes this by introducing a chirp subcarrier. So before we have the OFDM, which are multiplexing symbols onto this chirps, onto the subcarriers, and the AFDM now, which are using what is called the inverse discrete affine Fourier transform, multiplexes the symbols onto different chirps. And each of the subcarriers are different chirps at different frequencies or different combinations of the chirps. And this chirp is formulated by what is called this inverse discrete affine Fourier transform. And it's given by this A matrix, which is simply a Fourier transform matrix, left and right multiplied by two diagonals. So this diagonal matrix, which is composed of a chirp sequence. So we can see that this lambda, capital lambda, of a given frequency C of I, we have this diagonal which is consisting of a chirp matrix. And this chirp sequence, we can see that the subcarrier behavior in over frequency and time, the OFDM behaves as we know with the conventional structure, with each tone, each subcarrier lying on the same frequency over time. But now the AFDM has this subcarriers which are changing in frequency over time, of course, with proper wrapping. And this chirp rate, so the slope of these chirps is determined by the C1 parameter, as we will see in more detail later. But the C1 factor determines how slow or how fast these chirps are changing over time. And on top of this, AFDM, because the subcarriers are also lying on a chirp, they require a special type of prefix, which is called the CPP, or the chirp periodic prefix. And this is basically identical to the OFDM prefix, but now because notice that if you assume, of course, for the visualization, I have not wrapped them, they have to have another phase correction, which is where our previous phase shift function comes from. And this is simply given by this phi of CPN function here, which is dependent on the phase slope factor that we saw before, C1, and then also these dependent on the size of the matrix. We have this correction terms, and this phase is applied to the elements that are applied in the prefix. So given that, we can go back to the AFDM over the doubly dispersive channel, and we can see the effect the effect of the effective channel on basis to the Fourier of the Doppler shift and the delay shift. So here we have the IDAFT or the DAFT, the forward one described by A of n. The effective channel simply is multiplied by the inverse inverse affine Fourier transform and the forward Fourier transform on the left. And this gives us the AFDM effective channel. And now going back to the same type of analysis we have done with the Fourier conjugation, we want to now do the affine Fourier conjugation. And we can also, for the sake of this example, we can take the chirp prefix matrix to be identity, which actually happens when the term 2 times n times the chirp rate C1, the slope. If this is an integer value, this chirp prefix also collapses to identity. Of course, we can include this, but for now, for the sake of derivation, we also assume this case. Then we have this form as we saw before with the last terms that are corresponding to the chirp structures. And then we also take now the first analysis that we've done before. We conjugate the middle part, so here, with not the Fourier matrix, but with the chirp matrix. So this chirp diagonal is conjugated because these two are identity, that they are also unitary matrices. And then we also take the diagonal of the W. So now we have replaced this inner 4 matrix into 6 matrices. And now we have conjugated the diagonal matrix and the shift matrix by the chirps. And what happens when you take the conjugation, this diagonal matrix simply does nothing because this is a unitary transform with no column-wise transform. So it's simply the exact same matrix. But now this shift matrix has some change, which is that on top of the shift that it had before, we also have this additional chirp-based phase ramp that is given by the W we saw before, the roots of unity. The power of this term dependent not only on the chirp rate, but also on the Doppler. So we have this term appearing and also some global phase. And when we multiply these two matrices together, what we get is this total effect of the inner matrix, which is some global phase that we can take out for some now. But compared to the previous step we had before, this f of p, we now have an additional term in the phased ramp, which is called the Doppler shear. So now before we had a pure f of p, and that results in a nice grid over the delay and Doppler. But now each of the Doppler terms are sheared or scaled with respect to the factor C1 and also this delay as well. So now every Doppler is dependent on the sheared proportional to the delay and also with the factor. And illustratively, this can be seen by on the figure on the right. So normally we would have a gray grid, which is uniform over the delay and Doppler indices. But with this shearing, this grid is now transformed to this stretched or twisted version of the same grid. And this is also why we have this affine notion of this waveform. This shearing happens, and all of these taps in the delay Doppler are being scaled correspondingly in the grid. So that is the illustration of what happens when we conjugate the inner two matrix, the shift matrices by the chirps. And that's why the C1 determines the chirp rate determining frequency appears in the exponential. And now we want to see the effect of the Fourier conjugation of this exact same thing, which is actually identical to what we saw with the OFDM case, except for this Doppler shearing. So now we have a unit delta for the integer case at minus f plus this shearing term, and also for the same with the fractional case with the fading leakages around the diagonal, which happens at this factor p f of p plus 2n c1 of lp. So now this is both dependent on the delay and Doppler. And now actually when we now assume the integer case, so just the first part, and the Doppler is maximized and limited to the maximum Doppler and the minimum Doppler as f max, which is also integers, and also the delay, normalized delay is of course also integer. We can set C1 to be this value, so 2 of f max plus 1, 2n, and this actually comes directly when we input this C1 parameter into this Doppler shearing factor. So when we replace the C1 by this, what we get is that we ensure that for integer Doppler and integer Doppler case and the integer delay case, that this shearing factor here, Fp plus 2 and C1 of L, is always going to be integer because we have now set the corresponding parameters. And that means that we always get the unit delta response, and which means that we only get the shift, deterministic shift based on the Doppler and the delay terms. So this is also one of the main conditions of the AFDM to ensure full diversity, as we'll see. So now, given that we have ensured that the Doppler shear term will be purely integer, that we can denote this as a Doppler shearing shift with the pi matrix. And now finally, we can also rewrite the final outer chirp effect by the C2 chirp. This is only, again, a similarity transform. So the C2 appears only in the phase affecting terms, so the global phase, and also the Doppler phase ramp. Then we have performed this optimization of the C1 parameter, which is an integer. And also for the sake of further notation, we define this Q of P, which is the Doppler shearing factor, as we saw before. We can rewrite the total effective channel of the AFDM into three parts: the global phase, which is dependent on both all of the parameters, the delay, the phase, and the C2 parameter. But in the end, this is not really relevant because it's a global phase. And the circular shift, which is only dependent on this term Q of P, and then a phase ramp, which is dependent both on the delay and the chirp parameters. So this, now we get the final input-output relationship between the AFDM input signal and the output signal, which is a phase ramp of a given slope determined by some complex factors between the delay and Dopplers. And then the important is that the left circular shift by minus of QP, which is determined by the Doppler shear factor we had before, and then some global phase, and then the complex fading. And the important part to notice here is that now the circular shift is no longer just with the Doppler shift that we saw before, as with the OFDM, but now we have another term that is dependent also on the delay, the L of P. And because this L of P is multiplied by the maximum width, negative and positive side of the Doppler, which is f of max, all of the different integer delay and Doppler will lie on different unique shifts. That means no paths will overlap if they have different Doppler and different delay. And that means we get for the AFDM a full multipath diversity guarantee. And this is one of the strongest advantages of AFDM. So given the previous derivations, we can also now see the effect of C2. We saw that C1 had to be optimally parameterized to get the full diversity, but now for C2, we see that this affects the phase ramp of the slope and also the global phase. And this does not affect the grid itself, as we mentioned. This does not change the shift factor. Therefore, it does not affect the orthogonality or the diversity conditions of AFDM. But what it does change is now the phase ramp, and this means that we have to set C2 some at least to ensure that the Plei's phase does not wrap around and becomes periodic, and that this has some aliasing. So the easy way to ensure this is by simply setting C2 to 1 over 2n, such that it cancels out and it lies in a perfect period. Or we just set C2 to be some irrational value such that periodic aliasing cannot happen. So these are the two not optimal conditions, but at least the minimal conditions of the C2 that has to be set to ensure the full uniqueness of the different samples and the paths. So finally, we can see what happens of the channel in comparison to the OFDM. Let's assume that we have 3 paths and we have some maximum Doppler shift of 4, integer value 4. We have 3 different paths that are denoted by this red, single delay and no delay and no Doppler. So this will line the origin, so the central diagonal. In the second path, we'll have single delay, so delay of 1, and then -2 of Doppler shift. And then the third path will have shift of 3 and a Doppler shift of 1. So for the OFDM, the only thing that changes this shift is the minus Doppler. So we can see that each path is lying on a diagonal position, and we can see that this position correctly corresponds to the value of f. So this yellow path is the third path. So +1 is, so this is a left circular shift. So this is why it's lying on this correct position. And the delay does not do anything with the shift. But now what we see with the AFDM is that the paths are much more spread out because of this delay-dependent guarding term on top of the Doppler shift. And this position is also uniquely determined by the term QP. For our case, this f of max is 4, so we have 2 times 4 plus 1, 9. So each integer shifts the matrix by 9 terms. And then we also have this Doppler term, which now in the blue case is -2, so we have a total shift of 7. And this is what the effect of AFDM does. And one thing that you can clearly see from here is that because all of the delayed Doppler paths are uniquely lying on different diagonals, one can extract, so kind of reverse engineer this L and F factors from Q to get the integer Doppler and delay factor. So if we, for example, estimate the channel and take the first row or first column, that means each of the positions of the diagonal, if we take, in this case, the modulus to 9, modulo 9, we get the value of FP. And then if we subtract that FP and then divide by 9, we get the value of LP, which are exactly the equivalent radar parameters, which can be translated correspondingly to the scattering range and the scatter velocity. This is why the AFDM is so beneficial for the ISAC case as well. And then when we have fractional Doppler shift, we mentioned that we get a Dirichlet-based leakage around the main diagonal. So the position of the main diagonal is the same as we saw before, depending on the delay and the Doppler and OFDM and the AFDM, we saw the same positions. But now we have a fading around, or this leakage around the diagonal. And this leakage is maximum when the fractional part is equal to either plus or minus 0.1. Of course, there's no leakage means it's 0, and this is clearly because this plus and minus 0.5 is lying exactly between the two integer taps, such that they will have maximum leakage or interference between the two taps. So this is the structure of the effective channel when we have fractional fractional Doppler shifts and integer delay. So in the end, this first part goes over the outlined topics, the channel model, the signal processing, and the full input-output relationship, which we also summarized using a schematic diagram. And then finally, the effective channel analysis of OFDM and its challenges, which you saw with the diversity and the inter-carrier interference. And then the upgraded version of OFDM, the AFDM, and its benefit due to the chirp-based scaling, the Doppler shearing in the end, and that ensures full diversity guarantees in both the delay Doppler. So in the next two parts, we'll now see, in part 2, we see focusing only on the AFDM. We delve more into its properties and its benefits in comparison to the OTFS especially, which is also known for good performance over doubly dispersive channels. And finally, also some standardization perspectives of this waveform. And then part 3, we will also look at enhanced waveforms again, that is based on this fundamental sub-carrier wise chirp of the waveform. So that's it for the presentation, and thank you very much.
Thank you, Eric. Thank you very much. Guys, questions? Don't be shy. Anybody?
I
Edward,
have
go ahead.
I have a question.
Yep.
So maybe you will mention this in the later part, but from my expertise, I know that OFDM suffers from PAPR. Can you just shortly elaborate what is the deal with the AFDM in this case?
Right. So that's a good question. So we know that the OFDM does not have very good PAPR, and AFDM, as we saw, in terms of the formulation of the modulator is left and right multiplied by these chirp matrices, and these are actually just unitary transforms. So it does not have any effect on the PAPR fundamentally. So the baseline AFDM, as we described here, will have the exact same PAPR performance as the OFDM. But the enhanced waveform that is shortly outlined in the other two So part 3 of this chirp permuted AFDM and the affine filter bank modulation adds on top of this AFDM in light of the freedom that we have with the chirp parameterizations. This actually enables a decrease in the PAPR in this sense.
Okay, so but from what I understand, when you say that AFDM is just left and right multiplied by symmetries, does this mean that most of the PAPR algorithms that work for AFDM will work for AFDM at the end of the day? Is it
Exactly.
Okay.
So so tone-based, for example, or filtering or windowing, all of these PAPR techniques that are working with OFDM will work exactly also for the AFDM without major changes.
Perfect? Thank you.
Yep. Thank you. Any
Thank you,
other
Getwa.
questions?
No? Okay, well, if not, thank you very much, Eric. I'm sure guys have questions, but maybe they are shy to do. But that's
Yeah.
it anyway. It's an amazing amount of work. So thank you very much once again, and I see you next time in the wireless channel.
All right. Thank you.
Bye, guys.